Minerals in food. In this topic, we will cover definition, classification, and sources of mineral, physicochemical properties, biological functions and bioavailability of minerals, technological functions, and effective processing on mineral and fortification. At the end of the topic, students should be able to classify different types of minerals, explain the chemistry and functions of different types of minerals, and comprehend the effect of food processing on stability of minerals. Definition of mineral. It refers to inorganic elements other than C, H, O, and N that are present in food. These four non-mineral elements are present primarily in organic molecules, and water constitute about 99% of the total number of atoms in living systems. Mineral elements are present in low concentrations in foods. They play key functional roles in both living systems and foods. Minerals do not contribute to energy to the diet. Minerals are classified into two groups: major minerals that need to be consumed in more than 100 milligrams per day. The examples are sodium, potassium, chloride, calcium, phosphorus, magnesium, and sulfur. The second group is trace minerals that need to be consumed less than 20 milligrams per day. The examples are iron, copper, zinc, selenium, iodine, chromium, fluoride, manganese, molybdenum. These are the examples of different sources of different minerals. Moving on to the physicochemical properties of minerals. First aspect is solubility in aqueous system. In nature, most nutrients are delivered and metabolized by organisms in an aqueous environment. The availabilities and reactivities of minerals depend on their solubility in water, and the species of elements present in food vary considerably depending on the chemical properties of the element. Elements in groups 1 and 7 in Figure 9.1, which is in the next slide, exist in foods as free ionic species. They are highly water-soluble and have low affinities for most ligands. Thus, they exist primarily as free ions in aqueous systems. Most other minerals are present as weak complexes, chelates, or oxygen-containing anions. The solubilities of mineral complexes and chelates may be very different from the solubilities of inorganic salts. For example, if ferric chloride is dissolved in water, the iron will precipitate as ferric hydroxide. The elements mentioned before are in the red boxes. Second aspect is acid-base chemistry. Much of the chemistry of the mineral elements can be understood by applying the concepts of acid-base chemistry. Acids is H+ ion and bases is O ion influence the functional properties and stabilities of other food components by altering pH of food. Thus, acid-base chemistry is critically important in food science. The Lewis acid-base concept is key to understanding the chemistry of minerals in foods because metal cations are Lewis acids and they bind to Lewis bases. The complexes resulting from reactions between metal cations and food molecules range from metal hydrates to metal-containing pigments such as hemoglobin and chlorophyll to metal enzymes. This slide is just a recap on what is Lewis acid and Lewis base. The interaction between them produces acid-base adduct. Third aspect is chelate effect. A chelate is a complex resulting from the combination of a metal ion and a ligand. They can form two or more bonds together that result in ring structure that includes the metal ion. Chelates are very important in foods and biological systems. In food system, chelating agents may be added to sequester mineral ions such as iron or copper to prevent them from acting as pruxidants. In addition, perform chelates, such as EDTA, a popular chelating agent that is being added to foods. Chelating agent is a molecule that can form several coordinate bonds with a single metal ion. The functionality of chelating agent depending on their ability to bind metal ions, which has contributed significantly to the stabilization of food color, aroma, and texture. As mentioned before, the most important chelating agent in the food industry is EDTA. Other two important chelating agents, ethylenodiamine and dimercaprol. They promote color retention on dried bananas, beans, chickpeas, canned clams, pecan pie filling, frozen potatoes, and canned shrimp. Please bear in mind that chelating agents are not antioxidants. They serve as scavengers of metals which catalyze oxidation. However, trace elements such as iron, cobalt, and copper often accelerate the deterioration of foods and can act as catalysts for fat or oil oxidation. For example, ascorbic acid, vitamin E, thiamine, and folic acid are affected by copper. Copper and iron led to the destruction of natural and added vitamin A. Trace metal ions in foods can produce undesirable effects such as discoloration, turbidity, and oxidation. pink discoloration in canned pears, blue-green in shellfish and arthropods, gray-bean in canned maize, clouding of soft drinks, and chill haze in beer is caused by trace minerals. Their binding by chelating agents increases antioxidants efficiency and inhibits oxidation of ascorbic acid and fat-soluble vitamins. Minerals work together to perform important functions in the body. Generally, their important biological functions are fluid and electrolyte balance, blood formation, building healthy bones, and maintaining a healthy immune system. Table 9.2 summarizes more specifically the biological functions of each type of mineral, its deficiency effects, adverse effects from excessive intake, and food sources. Some minerals work together to form similar functions, while some minerals have their special function in our body. For example, iodine has special function in our body system as it is required for synthesis of thyroid hormones. While some minerals like lead, mercury, and cadmium are not essential nutrients and have no function in our body system. However, the excessive intake of them will cause adverse effects to our health. Bioavailability of minerals is the degree to which a nutrient from food is absorbed and utilized in the body, or proportion in ingested food that is available for utilization in metabolic processes. It's determined by efficiency of absorption from intestinal lumen into the blood. Absorbed nutrients may be in form that cannot be utilized, vary 1% to greater than 90%. Table 9.5 summarizes the factors that may influence mineral bioavailability from foods. They are mainly the chemical form of the mineral in food, either higher soluble or chelated form, food ligands, redox activity of food composition, mineral-mineral interaction, and physiological state of individual. Moving on to the technological functions of minerals in food processing, we will see the functions according to different minerals. First is cadmium. Functional role of calcium in milk and milk products has been studied extensively and serves as an example of mineral interactions in a food system. In cheese, calcium and phosphate play an important functional role in the manufacture of cheese. Addition of calcium prior to renneting shortens coagulation time. Curds with lower Ca content tend to be crumbly, while cheeses higher in Ca are more elastic. In vegetables, calcium salts are widely used in the fruit and vegetable industry to enhance texture. Calcium ions, which are divalent, can slow the decline in firmness in fresh-cut fruits and vegetables by forming. Phosphates occur in foods in many different forms, both as naturally occurring compounds intrinsic to plant and animal tissues and as components in food additives. Phosphate food additives serve many functions, including acidification, buffering, anti-caking, leavening, stabilizing, emulsifying, water binding, and protection against oxidation. The chemistry responsible for the wide array of functional properties of phosphates is not fully understood, but undoubtedly is related to the acidity of protons associated with phosphates and the charge on phosphate ion. Sodium chloride, or our table salt, plays an important role in controlling microbial growth, improved water holding capacity in meats, and enhanced color. It adds flavor as a single ingredient and enhances other flavors in foods and reduces bitterness. In processed meats such as sausages, salt acts as preservative by lowering water activity, promotes the solubilization of muscle proteins that then function as emulsifying agents. In bakery products, salt enhances flavor without imparting a salty taste, controls the rate of fermentation in yeast leaven products, dough improver through its interactions with gluten protein. Copper, like iron, is a transition element and exists in foods in two oxidation states, Cu+ and Cu2+. Both Cu+ and Cu2+ bind tightly to organic molecules and thus exist primarily as complexes and chelates in foods. On the negative side, copper is a potent catalyst of lipid oxidation in foods. Many recipes for meringues specify copper bowls as the preferred vessel for whipping egg white. Common problem with egg white foams is collapse resulting from overwhipping. Foam stability is reduced when the proteins at the air-liquid interface are excessively denatured by whipping. Egg white contains canalbumin, a protein analogous to the plasma iron-binding protein, transferrin. Canalbumin binds Cu2+ as well as Phe3+. And the presence of bound copper or iron stabilizes canalbumin against excessive denaturation. Moving on to the effects of processing on minerals in food. Minerals, unlike vitamins and amino acids, cannot be destroyed by exposure to heat, light, oxidizing agents, extremes in pH, or other factors that affect organic nutrients. In essence, minerals are indestructible. Minerals can, however, be removed from foods by leaching or physical separation. The most important factor causing mineral loss in foods is milling of cereals. Mineral elements in grain kernels tend to be concentrated in the bran layers and the germ. Removal of bran and germ leaves pure endosperm, which is mineral poor. Similar losses occur during milling of rice and other cereals. These are substantial losses. During fortification of milled products in U.S., iron is the only mineral commonly added. In cheeses where the pH is low, substantial losses of calcium occur when the whey is drained. Since many minerals have significant solubility in water, it is reasonable to expect that cooking in water would result in some losses of minerals. In general, boiling in water causes greater loss of minerals from vegetables than steaming. Mineral losses during cooking of pasta are minimal for iron but more than 50% for potassium. In U.S., most foods containing refined cereal grains are enriched with iron, niacin, riboflavin, thiamine, and folic acid. Current FDA standards for enriched flour, bread, rice, corn, and macaroni products are listed in Table 9.14. In addition, calcium, zinc, and other trace minerals are sometimes added to breakfast cereals and other products. Infant formulas contain the largest number of added minerals since they must be nutritionally complete. Most salt destined for domestic use is iodized. Universal salt iodization is a key strategy proposed by WHO, UNICEF in 1198 in eliminating iodine deficiency disorder at the population level. The objective of the Universal Salt Codification Program is to control and prevent iodine deficiency disorder, especially among vulnerable groups such as pregnant women and children. It is implemented by adding iodine to the salt sold and marketed to the community. In November 2018, the whole of Malaysia has been gazetted to use iodine salt mandatory for household use and will take effect from the 30th of September 2020. Household salt is chosen as a medium to implement the process of iodization. Why do you think household salt is chosen to combat iodine deficiency among Malaysians? Please join the discussion on this issue at the PUTRAMOOC platform. To conclude, by now you should know what is mineral in food, different classes of minerals, sources, technological and biological functions, and how the amount of minerals in food is affected by the processing and fortification to achieve the daily requirement of minerals in our daily diet. Here are the references. Thank you.